This video shows some additional work I've done on my MAXI09OS. So I'm SSH to my Linux box, which is where I do my development, because everything is cross-compiled. And I'm running tmux, which I've just started using after being a long time screen user, so I may get some of my keyboard shortcuts wrong. And I've got 3 sessions. This one is the shell for the MAXI09OS, which I showed you in the last video, except in that video I was using the console, but all the time that the console shell is running, I'm also running the shell via a UART port. So this is normally how I interact with MAXI09OS. In fact, usually I play with the board from another room using my laptop. I can flash the EEPROM, work on the VHDL, do everything I can remotely pretty much, except of course play my Snake game and things like that. So what I've got here is the shell. I've also got the file server program. This is a very simple little C program that listens on a second UART port on the file server for a command from the MAXI09 board for a file. So it's a very simple protocol. It's literally here's a file name, here's the data, and with a file size that's sent before the data, so that the MAXI09 board can allocate enough memory to hold that file. And then I've got a standard bash shell, so I can, assuming I've actually remembered to compile it, I can download, what is it called, test.bin, yeah, so I can download a the same test program I ran from Compact Flash in the previous video. I can download that through the UART. So just to show you how quick it is to modify that code and run it on the board, I can, there we go, there's the file server serving out that file. I can modify that program. Here it is. It's pretty simple, obviously, because it just asks for a few strings and calls to different MAXI09OS routines through a jump table that was the start of the EEPROM. The point of that is so that I can rebuild the EEPROM without having to also rebuild any user code. So all of the OS routines are basically exposed for a vector table. So I can just go and change this little program here, change a string, change the prompt to the program asks for, save that, run make to rebuild it, which is using ASXXX with a wrapper, because the AS609 assembler doesn't seem to deal with failures very well. It leaves the result around, so I have a wrapper that cleans it up if the build fails, otherwise make gets very confused. And then of course I'm turning the Intel hex into a binary. So if I go back to Minicom and I run that again, there you go, change the prompt. That's that. I like my little file server. It's a much quicker way to try out code than having to copy files to the Compact Flash and move the flash around and risk bending the pins, because the Compact Flash ports, whatever you want to call them, are not particularly sturdy. So then we've got C code. So C code's a little bit more complicated, because I need a way to call the OS routines that are exposed through that jump table from C. And traditional C compilers follow the pattern of pushing all the parameters onto the stack. I think that's what the first C compiler ever did. Obviously it's not particularly efficient, and any decent compiler will, not that CMOC isn't decent, will generally try to use registers. But anyway, so I can show you how I wrap implementing MAXI09 calls through that jump table in a C function. So this is a module that effectively declares C functions for the MAXI09OS subroutines that I want to expose, and like the rest of this C build system that currently supports either GCC or CMOC. I won't talk about GCC for now, but we have here the inline assembly for the sysopen call. So we push A and B onto the stack because we modify those, because we need to set those registers from parameters passed through the stack. So we load the device name, which is normally UART or IDE or LED or whatever the other device is that I've implemented the driver for, set the two parameters, and then jump through the vector table to the sysopen implementation inside the EEPROM, and then I save out the X register into the device variable, which is also on the stack, and then that's returned. So that's how assembly code is wrapped from a C for a C function. And I've got various other MAXI09OS routines that I've wrapped in a similar way. I've not implemented all the wrappers because MAXI09OS has got many functions for everything. Just enough to play with and prove the theory that I can write little C programs. So there's put string def.io, which is used quite a lot to put a null terminated string out on the task's default I/O device, which is my sort of alternative to standard I/O. Well, sorry, standard in and standard out and standard I just have a single device that's a property of the task structure, and def.io, all these functions that in def.io use that preference to explicit device. So in the put string def.io for CMOC, again I push the parameter onto the stack that I'm modifying, load in the parameter that's passed in to that subroutine, and then call the assembly subroutine through the vector table. So this libc directory here just contains a scant few C library functions that I've implemented. These are basically the absolute trivialist implementation for these types of functions. So it's space, and I don't think that's correct, because I think the standard defines this space as white space, not just an ASCII space, decimal 32. But the plan is to eventually build up a complete enough but at the same time very minimal C library, which is good enough to build up to build simple programs. So we've got the example directory. So here's my I/O program. It's just test I/O. What is your name? Blah blah blah. I've got multiple implementations of this type of program. I think there's even a task. Well, there is a task, isn't there, on the second console that does this, and it's got different names, which is quite confusing. In this C implementation, I've called it io.c instead of test.c, which is more logical following on the assembly version name. Anyway, so, and even this string differs between which version is being run. I should probably introduce some consistency. Anyway, so if I go and build that program, so that will be called io.bin in user C examples io. code.bin. There we go. And we got, just quickly show you a slightly more complicated example. This is my prime number program. So I'm not using printf here because I haven't implemented it. But I am using smprintf to print into a buffer. So that's how I'm printing decimal numbers from MAXI09. I've waited about 5 years to see any 6 out of 9 code produce decimal numbers. I really need to implement the algorithm myself just to understand it. So that's about it for the C stuff. I'll quickly show you the make file actually, it's kind of cool. So this is my header make file that all of the directories containing C code reference to get these C flags and the particular compiler. So I call it a toolchain here, GCC or CMOC, and if you're using GCC it sets CCLD and AR variables appropriate, and then if you're using CMOC it sets them to CMOC values, and CMOC uses LWASM I think, or LW tools, I can't remember what it's called, but a different assembler to what I use to build the rest of MAXI09OS, which comes from the ASXXXX suite. So switch back to the shell running on the UART, and what I should do now is enter my debug monitor. So you can either enter that via the console or via the UART, and in the case of using the console you press Shift and Help, because I'm using an Amiga 600 keyboard, and the Amigas were kind of funny in that they had a button labelled Help. Never actually did anything on any Amiga I've ever used, but that's the button I chose to enter the debug monitor. Or on the UART you send the break sequence, so I'm going to send that using Control A and F on Minicom. So I'm in the monitor now. So for the time that the monitor is active, task switching is disabled. So none of the tasks, or rather, the only task that's running is the one that's running the monitor, which is the one that you were using when you entered it. So the purpose of the monitor is it's got a few different uses. One is for very low level stuff like dumping out memory. That's dumping out the first 128 bytes of the EEPROM. It's also used to examine OS data structures like the tasks list or lists. So you can see those are the tasks in the system. We've got the timer task, which is the thing that listens on the timer, and the keyboard and the joystick now, and that's the thing that's running on the first console, which you normally see at the start of the videos I've made. Then you've got the shell running on UART 0, which is the task that I'm interacting with now. Then there's some waiting tasks. So you've got init, which is the one that started at the system startup time, which then starts the other tasks in the system, all through assembly code at the moment. And then you've got two console shells. So I've got two console shells running on console 3 and 2. And then there's the echo task, which is the one that waits for a name and it echoes it back out again. And then there's the idler task, which is the one that runs when there's nothing else to run. Oops. So although task switching is disabled, the interrupt handlers are running, and it's the interrupt handlers themselves that move the task between the say the waiting list and the ready list. So in theory, if I interact with the let's say the shell running on console 2 by pressing a key, that should move that task to the ready set. Now of course you can't see the console, but I shall press the button now, reload that. So I had to first switch the active console using the F key, and then I pressed another button. So if I run the task command again, there you go, you can see that shellcon2 has now moved over to the ready set. So when task switching resumes, which will happen when I leave the monitor, that task should then start running and pull the key press out of the buffer that the service routine put there. So I can also show details about a particular task. So if I show the details for that task that's entered the ready queue, the ready set rather, 1DBA. There we go. So you can see the parent task, which is the structure is at 0EB5, which should be a NIT. Yeah, there's a NIT. Dispatch counts how many times it's been run. The default I/O device for that particular task. The current directory inode number. The system presently only supports a single mounted file system, so the current directory is literally just that inode number. The initial program counter, which is just another identifier for the task, essentially. It points to the first instruction that's run when the task was started. The saved stack register, which is in RAM obviously, and the signals allocated, signals weighted, and signals received. So that that bit 0 allocation and weighted and received will be the console, because I hit the button on the keyboard, and then you have the registers that were stacked. I also have a crude but serviceable disassembler. The code for this was written a very long time ago, and I did a very quick port of it to run under MAXI09OS. Given what I've learnt about 609 since I wrote this, I would probably write this quite differently. The code is also rather large, and it's starting to, my EEPROM is now starting to get filled up. I only have about 2 kilobytes free, so if I had time I would probably rewrite my disassembler, but nonetheless it's serviceable. So I can disassemble let's say we disassemble this particular task code. So we start at the initial program counter, which was DD1F, and the second parameter is the number of opcodes to disassemble from. So we'll do 16 opcodes, because of course all these parameters are in hex. And that's the disassembly for that shell, and obviously you've got no labels or anything in here, so I couldn't actually tell you what most of this does. But the disassembler was an interesting thing to write. Yeah, they're sometimes useful. So we can also write to memory. So I know that 700 hex should be unused by the system at this point. So I can write some strings in there. Write some values in there. Now we'll have a one ball. So the parser that the shell and the monitor uses, so I think it's quite cool. I've seen monitors that were available at the time that 609 was released, and they seem very, very crude. so we can the MAXI09OS parser can pull out effectively arbitrary sequences of bytes, words, and strings, and those effectively go into a list, which the implementation for the particular command then scans down and with effectively a type value followed by the value, you can form up the parameter strings. So that will write those things into memory. So we've got a byte and a word and the ASCII womble string. So mostly these types of commands, especially the read byte command, can't type today. They're mostly used to interact with registers, either in the on the board on those discrete ICs like the 6522 or the say the UART or the joystick port or whatever. So I usually sorry, I lost my train of thought there. I usually use those commands to interact with those ICs as opposed to memory. And in fact, I don't really use the low-level commands very much. I mostly use the monitor for playing with drivers. So I can using the monitor commands, I can open a device, passing the parameters. I can close the device. I can read and write bytes. I can read and write blocks from the IDE port, and I can send arbitrary control commands which route down to the particular device and do something like read the MBR if it's the IDE device you're talking to. And the main reason I implemented those functions inside the monitor was to make debugging of the device drivers possible, because otherwise I was kind of writing things blind. So what I wanted was a way to individually step through and exercise the driver commands. So for instance, when I was writing the IDE driver, I never actually interacted with the IDE device outside of the monitor, because I didn't have to. The monitor was adequate to prove that the code was working. I could read disk blocks, I could read the MBR, I could send the identity command and read out the response from the attached compact flash, all within the monitor. Otherwise I'd have had to go writing little test scripts or little test programs and running those. So those I'm sure those commands inside the monitor will serve me in the future when I write more drivers for things like the 6522, so I can do some fun 9-pin printing with my Citizen printer. Well, I hope you found some of that interesting. Feel free to leave any comments. Thank you for watching.